Hello, welcome to this video. Today we're going to prove this problem. So the question follows like so. So first we'll define order A of n to be the smallest natural number that satisfies that a to the power of order n. Order A of n is congruent to 1 mod n. For n to n being natural numbers and obviously co-prime. And because if they're not co-prime, there isn't a number that a to the power of it is even congruent to 1 mod n. So n and n are also co-prime to each other. We need to show that order A of n divides phi of n. And phi of n, just as a reminder, is the amount of numbers co-prime to n and not bigger than n. The amount of natural numbers, of course, co-prime to n and not bigger than n. So let's begin. So first of all, let's remind ourselves what property phi of n has with a to the power of something congruent to 1 mod n. It's actually a very direct relationship, which states, which we did prove recently in a video, that if a and n are natural numbers and are co-prime to each other, then a to the phi of n is congruent to 1 mod n. We proved that. That is a fact. And now order A of n is the smallest natural number that satisfies this property. We want to show that order A of n actually divides phi of n. So let's first of all write this. A to the power of order n a is congruent to 1 mod n. At least what I first thought to do here is maybe we'll try to do contradiction. Because usually when you have let this number be the smallest natural number that satisfies blah blah blah, then you want to show that this number makes this number satisfies a certain property. You usually incorrectly assume that this property is not satisfied, and then you get to a contradiction, meaning that this property is satisfied. And the usual way of contradiction is that you show that even though this is the smallest that satisfies, you can find a number that's even smaller that satisfies it. So that's what we're going to do today, and that's exactly what we're going to do. So let's begin. Let's assume. Assume the order of A of n. Order A of n does not divide phi of n. And we want to find a contradiction which is not surprisingly we'll be able to find a smaller natural number that satisfies this property, which will contradict that order A of n is actually the smallest one. So that's our assumption, and this means that if we do, because we have this mod going on, and maybe it will help, and maybe with those we'll be able to get a new number, maybe by subtracting and stuff from these exponents. Maybe what we can say from this is that now we know that phi of n mod order A of n is not 0. Of course, it's between Of course, it's between 0 and order A of n. Now we know it's not 0. Otherwise, order A of n, obviously, really by definition, would have divided phi of n. So now that we have this, we can say that there are two numbers, r and p, that are natural numbers that satisfy that r plus p times order n of a is equal to phi of n, and such that r is actually phi of n mod order a of n, meaning that r is between 0 and order n of a. But now that we know that this cannot be 0, and this is actually just r, now that we know that this is r, we can say that we can now remove this equal sign. So actually, I should say r and p are from z, that they're whole numbers. But because we know order a of n is so first of all, obviously p would be a natural number, really by definition of mod, and of course phi of n is bigger than order a of n, because order a of n is the smallest natural number that satisfies this property. And because phi of n does satisfy this property, obviously phi of n is bigger than this number, bigger than or equal to this number, meaning that yes, with certainty p is a natural number. And obviously, if r is a whole number but it's not 0, of course it is a natural number. So yes, we can say this is a natural number. So now, that we build this, now we can get to the contradiction. And because we can see r is a natural number and is smaller than order a of n, it could very well be the case, and actually is the case, that r is the number we're looking for to make a contradiction with. And this is how we do it. So now we know that these two properties hold. This, by definition, this is Euler's expansion to Fermat's last little theorem, which we did prove. And now we can substitute this into phi of n. So now we can say a to the r plus p times order a of n is congruent to 1 mod n. By exponent rules, we can turn this into a to the power of r times a to the order a of n to the power of p. So first of all, what we did is obviously this plus turned to this times a to the power of this and this to the power of this, and then this p turned into this exponent. So we got this, and I got up the exponent. This is still congruent to 1 mod n. We haven't changed anything, we just moved things around. But now we know a to the order a of n is congruent to 1 mod n by definition. And if we're doing this congruent to 1 mod n, we can replace this with 1, because we're working in the world of mod n. And with rules of mod, we can, because this is congruent to 1 mod n, we can replace this with 1, because we are working with mod n. So that's the r times 1 to the p, but 1 to the power of any natural number is equal to 1, but 1 is neutral to products, so this is just a to the r is congruent to 1 mod n. And we got our contradiction. We found a number r that's smaller than order a of n, but yet satisfies a to the r is congruent to 1 mod n, which contradicts that order a of n is the smallest natural number that satisfies this exact property. So we can say this is a contradiction, meaning that our initial assumption was wrong, and so order a of n divides phi of n. Now, notice, phi of n isn't really special here. If we have any number like k that satisfies a to the k is congruent to 1 mod n, order a of n will still have to divide k. But another property we get that phi of n always satisfies this is that now we have sort of infinite numbers, because we have order n of 1, order n of 2, order n of 3, so on forever, and all of them divide this single number, which is cool, which is just another cool property of this. So we can, yes. And finally, that's it. If you want more problems like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it.